Astronauts on the International Space Station look down at Earth and see oceans, mountains, cities. And one thing that shouldn't be visible from 240 miles up, but absolutely is, a hole in the ground in Utah. Not a natural crater, not a volcano, a mine. The Bingham Canyon Copper Mine, the largest man-made excavation on Earth. This hole is 3/4 of a mile deep and 2.5 miles across. If you stood at the rim, downtown Salt Lake City would fit inside with room to spare. Every single day, workers remove 450,000 tons of rock from this pit. That's enough to fill the Empire State Building every single day. Today, we're going inside Kennecott's Bingham Canyon Mine to see how 100 years of digging created a hole visible from space and transformed the global copper industry. This is the story of the world's most productive copper mine. The story begins in 1863, when soldiers discovered copper outcrops in Bingham Canyon, about 20 miles southwest of Salt Lake City. For decades, small mining operations tunneled underground, following veins of high-grade copper ore. But the ore bodies were complex, twisted, difficult to follow. Mining was slow, expensive, and dangerous. Then came Daniel Jackling, a metallurgical engineer who looked at Bingham Canyon and saw something nobody else did. The entire mountain was ore. Not high-grade ore, only about 0.6% copper. Traditional wisdom said you couldn't mine such low-grade material profitably. Jackling disagreed. In 1906, Jackling convinced investors to try something radical: open-pit mining on a massive scale. Instead of tunneling underground chasing high-grade veins, they would remove the entire mountain, process astronomical volumes of rock, and extract copper from material everyone else considered worthless. It worked. The Utah Copper Company, which later became Kennecott, started digging. And they never stopped. For over 100 years, Bingham Canyon has operated continuously, 24 hours a day, 7 days a week, 365 days a year. Through wars, recessions, copper price crashes, even a devastating landslide. The mine keeps running. To understand the scale, you need to see it. The pit spirals downward in terraced benches, each bench 50 feet high. There are dozens of these benches, stacked like a giant amphitheater descending into the earth. The spiral road that trucks use to climb from the bottom to the rim is 22 miles long. 22 miles of switchbacks carved into solid rock. Standing at the bottom and looking up, the rim seems impossibly far away. The walls rise at carefully calculated angles, stable but steep. The deepest point is 3,900 feet below the rim. That's deeper than the tallest building in most cities is tall. Mining happens in a carefully choreographed sequence that runs around the clock. It starts with drilling. Massive rotary drills, mounted on tracked vehicles the size of houses, bore vertical holes into the rock. These holes are 40 feet deep and about 7 inches in diameter. Workers drill hundreds of holes in a precise pattern across a blast area. Then comes blasting. Crews pump thousands of pounds of explosives into the holes, connect everything with detonating cord, and evacuate the area. When the blast goes off, the explosion is carefully designed to fracture the rock into pieces the shovels can handle. Too big, and the shovels can't pick them up. Too small, and you've wasted explosive energy. After the blast, the loading shovels move in. And these aren't typical construction equipment. We're talking electric rope shovels that stand 7 stories tall and weigh over 3 million pounds. The bucket capacity is 98 tons. A single scoop fills a pickup truck bed dozens of times over. The shovels load the blasted rock into haul trucks, And here's where things get truly insane. These aren't trucks in any normal sense. They're 400-ton capacity mining vehicles that cost over $5 million each. The wheels alone cost $50,000 apiece and weigh over 11,000 pounds. That's heavier than 2 elephants per wheel. A loaded truck weighs roughly 800 tons. The engines produce 3,500 horsepower. And these monsters climb a 10% grade, carrying massive loads up that 22-mile spiral road from pit bottom to rim. Bingham Canyon operates roughly 29 of these trucks continuously. They run in a precisely coordinated ballet, each truck on a schedule, each driver in constant radio contact with dispatch. A single breakdown can disrupt the entire operation because the shovels need to keep loading and the trucks need to keep hauling. The trucks dump their loads at one of several destinations, depending on what they're carrying. High-grade ore goes to the concentrator. Lower-grade material goes to leach pads. Waste rock, which makes up about 60% of what comes out of the pit, goes to massive waste dumps that have grown into mountains of their own over decades of mining. The concentrator is where chemistry takes over. Crushers reduce ore to gravel, then ball mills grind it into powder. The powdered ore mixes with water and chemicals in flotation cells. Air bubbles cause copper minerals to float as froth that workers skim off. This concentrate, still only about 28% copper, travels by pipeline to the smelter. The smelter is a separate facility where extreme heat takes over. Furnaces operating at over 2,000 degrees Fahrenheit melt the concentrate. The molten material separates by density. Pure copper sinks to the bottom. Impurities float to the top as slag. The copper then moves to the refinery, where electrolysis produces sheets of 99.99% pure copper. These cathode sheets, each weighing about 375 pounds, stack for shipment to manufacturers worldwide. This copper becomes electrical wire, plumbing, electronics, everything modern civilization depends on. But Bingham Canyon doesn't just produce copper. The ore also contains gold, silver, and molybdenum. The mine has produced over 19 million tons of copper, 23 million ounces of gold, and 190 million ounces of silver since operations began. That's roughly 20% of all copper ever produced in the United States. The mine's history includes one of the most dramatic events in modern mining. On April 10, 2013, geologists monitoring the pit walls noticed accelerating movement. Cracks were forming. Rock was shifting. They ordered immediate evacuation of the entire pit and surrounding areas. On the night of April 10th, the largest landslide in modern North American history let go. 165 million cubic yards of rock, nearly twice the volume of the original Hoover Dam, slid into the pit. The ground shook like an earthquake. Dust clouds rose thousands of feet into the air. Seismometers detected the slide hundreds of miles away. Miraculously, nobody was hurt because of the early evacuation. But the landslide buried equipment worth tens of millions of dollars and reshaped the entire pit. Kennecott spent over a year removing slide debris, stabilizing walls, and rebuilding access roads before full production resumed. The slide was a reminder that open-pit mining at this scale pushes engineering limits. The walls are monitored continuously by radar, GPS sensors, and geologists who analyze every crack and movement. Modern technology allows prediction and prevention of most failures, but the forces involved are enormous. Environmental concerns have shaped modern operations. Bingham Canyon produces massive waste. Tailings ponds cover thousands of acres. Waste rock piles form artificial mountains. Kennecott has invested billions in environmental controls. When depleted areas close, reclamation begins with reshaped slopes, replaced topsoil, and native vegetation. The mine's future depends on copper prices and remaining reserves. Current projections suggest Bingham Canyon could continue operating for another 20 to 30 years. The pit might eventually reach depths approaching 5,000 feet. At some point, the economics won't work anymore. The ore gets deeper, harder to reach, more expensive to extract. But for now, Bingham Canyon remains one of the most productive copper mines on Earth. Roughly 1,500 workers operate the mine, concentrator, smelter, and refinery complex. Annual production varies, but typically runs around 200,000 tons of copper, roughly 2% of global supply. From Daniel Jackling's vision of massive-scale low-grade mining to today's computer-controlled operations, Bingham Canyon pioneered techniques now used at open-pit mines worldwide. The concept of processing huge volumes of low-grade ore efficiently revolutionized the entire mining industry. So next time you flip a light switch, charge your phone, or turn on your faucet, there's a decent chance the copper enabling that came from a hole in Utah, visible from space. A hole that's been growing for over a century. A hole that represents human engineering at its most ambitious and most audacious. From mountain to crater, from waste rock to pure copper. This is Bingham Canyon. Thanks for watching. Hit that like button and subscribe for more incredible stories about the largest, deepest, and most extreme industrial operations on Earth. See you next time. Picture this: a vessel longer than a football field, weighing nearly 8,000 tons, powered by a nuclear reactor that will run for 33 years without refueling. It can dive to depths where the pressure would crush a car like a tin can. It carries enough firepower to level a city. And it's so quiet, it's literally quieter than the background noise of the ocean itself. Building a nuclear-powered attack submarine is one of the most complex engineering challenges on Earth. Only 2 facilities in the entire United States possess the technology, security clearances, and expertise to do it. The construction process takes over a decade, costs $3.4 billion per vessel, and involves thousands of workers sworn to secrecy. Today, we're going inside those facilities to see how America builds the most advanced submarines ever created. This is the story of turning steel and science into invisible ocean predators. But first, we need to talk about the man who made it all possible. Admiral Hyman G. Rickover, a name most Americans have never heard, but who changed naval warfare forever. Born in Poland in 1898, Rickover immigrated to America as a child. He joined the Navy, became an engineer, and in the 1940s, he became obsessed with a radical idea: nuclear-powered submarines. The Navy brass thought he was crazy. Nuclear reactors were massive, dangerous, barely understood. Putting one inside a submarine seemed impossible. Rickover didn't care what they thought. He was famously difficult, demanding, and absolutely relentless. He personally interviewed every officer who wanted to serve on nuclear submarines. These interviews became legendary. He'd ask impossible questions, create uncomfortable silences, test people's breaking points. One future submarine commander reported sitting in complete silence for 2 hours while Rickover read paperwork. But it worked. Rickover built a culture of absolute excellence and zero tolerance for mistakes. In 1954, the USS Nautilus, the world's first nuclear submarine, went to sea. It revolutionized naval warfare overnight. Submarines could now stay submerged for months instead of hours. They could travel underwater at speeds conventional submarines could only dream of. Rickover ran the Navy's nuclear program for 63 years, longer than any military officer in American history. When he finally retired in 1982, at age 82, he'd built the foundation for everything we're about to see. Fast forward to today. The United States Navy operates the most sophisticated submarine fleet on the planet, and they're all built at just 2 shipyards: General Dynamics Electric Boat in Groton, Connecticut, and Huntington Ingalls Newport News Shipbuilding in Virginia. Let's focus on the Virginia-class attack submarine, the backbone of America's underwater fleet. These vessels represent the cutting edge of submarine technology. At 377 feet long and displacing 7,800 tons when submerged, they're massive. But size barely hints at the complexity. Construction doesn't start with laying a keel like traditional shipbuilding. Modern submarines are built in modules, massive sections constructed separately and then joined together. Think of it like building the world's most complex and expensive Lego set, where each piece weighs hundreds of tons and costs millions of dollars. It begins in fabrication shops across the facility. Workers cut and shape special high-strength steel called HY80, capable of withstanding extreme pressure at depth. These aren't thin sheets. We're talking steel plates 4 to 6 inches thick in some areas. Cutting and welding this material requires specialized equipment and certified welders who've spent years training. The hull sections start taking shape in massive assembly buildings. The submarine's hull uses a cylinder design, the strongest shape for resisting pressure from all directions. Workers install thousands of components inside each section before the modules get sealed. Piping systems, electrical conduits, equipment mounts, ventilation, all precisely positioned. Here's something most people don't realize. Submarine construction is measured in years, not months. A Virginia-class submarine takes 10 to 12 years from first steel cutting to delivery. Why so long? Every single weld gets X-rayed. Every system gets tested multiple times. One tiny defect in a weld could mean catastrophic failure at depth, where the pressure exceeds 800 pounds per square inch. The most critical and secretive module is the reactor compartment. This sealed section houses the S9G nuclear reactor, the beating heart that powers everything. The reactor details are highly classified, but we know the basics. It uses enriched uranium fuel, generates heat through nuclear fission, which creates steam to drive turbines, which generate electricity and turn the propeller. And here's the crazy part. This reactor will run for 33 years without refueling. The submarine will be retired before the reactor needs new fuel. That's the equivalent of buying a car that never needs gas for its entire operational life. Once the major modules are complete, the real challenge begins: joining them together. This happens in a massive indoor facility, where overhead cranes can lift hundreds of tons. Workers position each module with precision measured in fractions of an inch, then weld them into a single hull. The welding process is critical. Welders work in teams, often in cramped spaces, joining sections with welds that must be absolutely perfect. After welding, every seam gets ultrasonically tested, X-rayed, and pressure tested. The hull must be completely watertight, because at operational depths, even a pinhole leak would let water in with enough force to cut through steel. Next comes one of the most distinctive features, the anechoic coating. Workers apply thousands of rubber tiles to the submarine's exterior. these aren't decorative. Each tile is precisely engineered to absorb sonar waves, making the submarine incredibly difficult to detect. The exact composition and design of these tiles is classified, but they're a major reason Virginia-class submarines are quieter than the ambient noise of the ocean. Inside, the submarine is being fitted with systems that will keep 135 crew members alive for months underwater. The atmosphere control system is remarkable. It takes seawater, runs it through electrolysis to produce oxygen, and scrubs carbon dioxide from the air using chemical reactions. The crew breathes manufactured air hundreds of feet below the surface. Water systems are equally sophisticated. Distillation equipment converts seawater into fresh water for drinking, cooking, and the reactor cooling systems. A Virginia-class submarine produces thousands of gallons of fresh water daily, enough for the crew and all onboard systems. Food storage is carefully planned. Submarines carry enough provisions for 3 months, stored everywhere including under crew bunks. The galley operates 24/7, serving 4 meals daily to accommodate different watch schedules. Now let's talk about weapons. Virginia-class submarines carry a deadly arsenal. 12 vertical launch tubes in the bow can fire Tomahawk cruise missiles, capable of striking targets over 1,000 miles away with precision guidance. 4 torpedo tubes fire Mark 48 torpedoes, the most advanced submarine-launched weapons in existence. The torpedo room isn't just about firepower. It's where torpedoes are loaded, maintained, and prepared for launch. Each Mark 48 weighs nearly 3,700 pounds and costs over $3 million. The room includes sophisticated loading equipment, testing systems, and safety mechanisms, because you're dealing with high explosives in a confined metal tube underwater. The control room represents the technological heart of the submarine. Unlike old submarines with periscopes and mechanical controls, Virginia-class subs use photonics masts, essentially high-definition cameras on retractable masts that feed images to screens. The helmsman and planesman control the submarine using joysticks, not wheels and levers. Sonar systems fill an entire room with computer screens and sophisticated signal processing equipment. Trained sonar technicians can identify specific ship types from hundreds of miles away just by analyzing the sounds those ships make. The sonar sphere in the bow contains thousands of hydrophones working together to create an acoustic picture of the ocean. Communication at depth is challenging. Radio waves don't penetrate water. Submarines trail a wire antenna near the surface to receive very low-frequency transmissions. For two-way communication, they must come to periscope depth or surface. After years of construction, the submarine is finally ready for launch. But launching doesn't mean it's done. Not even close. The submarine enters a pier alongside the construction facility, where workers install final systems, load provisions, and conduct countless tests. Then comes sea trials, where the submarine leaves the pier for the first time under its own power. For weeks, the crew and shipyard personnel put every system through rigorous testing. Deep dive tests verify hull integrity. Speed trials push the propulsion to maximum capacity. Weapon systems fire test shots. Everything that can be tested gets tested. During sea trials, problems always emerge. A valve doesn't seal properly. A computer glitches. Instruments read incorrectly. The submarine returns to the pier, workers fix the issues, and trials resume. This process repeats until every system meets Navy specifications. Only after passing all tests does the Navy officially accept the submarine. A commissioning ceremony marks the submarine's entry into active service. From that moment, it becomes a Navy asset, ready for missions anywhere in the world's oceans. The construction process never stops. Electric Boat and Newport News are already building the next generation, Columbia-class ballistic missile submarines. These will replace the aging Ohio-class boomers that carry America's sea-based nuclear deterrent. Columbia-class submarines are even larger and more complex than Virginia-class boats. At 560 feet long and displacing 21,000 tons submerged, they're true underwater behemoths. Each will carry 16 Trident II. 2 ballistic missiles, each missile capable of carrying multiple nuclear warheads. The first Columbia-class submarine, the USS District of Columbia, is currently under construction with delivery scheduled for 2028. The program will ultimately build 12 of these submarines at a total cost exceeding $100 billion, making it one of the most expensive military programs in history. Technology continues advancing. Engineers are developing air-independent propulsion systems that could extend underwater endurance even further. New stealth coatings make submarines quieter. Advanced sonar can detect threats at unprecedented ranges. Automation reduces crew requirements. But some things never change. The fundamental challenge remains the same. Build a vessel that can survive in one of the most hostile environments imaginable, operate for months without support, and project American power anywhere in the world's oceans. From Admiral Rickover's vision to today's Virginia-class submarines, America has maintained technological superiority underwater for 70 years. Thousands of workers across 2 shipyards continue that tradition, building submarines that will patrol the oceans for the next 3 decades. So next time you look out at the ocean, remember, somewhere beneath those waves, a Virginia-class submarine might be passing by. You'll never hear it. You'll never see it. But it's there, a testament to American engineering and the thousands of skilled workers who built it piece by piece, weld by weld, over a decade of meticulous construction. From steel to silent hunter. Thanks for watching. Hit that like button and subscribe for more incredible stories about how America builds the most advanced military technology on Earth. See you next time.
Glass, it's in your windows, your phone, that beer bottle in your hand. But have you ever wondered how something so fragile starts as nothing more than sand? Today, we're going inside one of the most incredible manufacturing processes on Earth, where temperatures hotter than lava turn ordinary sand into the crystal-clear material that shapes our modern world. The story goes back over 4,000 years. Ancient Mesopotamians stumbled onto something amazing when they heated sand with certain minerals and got a transparent solid. But it was the Romans around 50 BC who really cracked the code with glassblowing. Then in 1608, English glassmaker George Ravenscroft changed everything by adding lead oxide to the mix, creating what we now call crystal glass. Today, the global glass industry produces over 130 million tons every single year, worth more than $160 billion. From smartphone screens to skyscraper windows, this ancient craft became absolutely essential to modern life. Let's head inside a modern glass factory and see how sand becomes glass. It starts in the batch house, where automated weighing systems measure each ingredient with precision down to 0.01% accuracy. The main ingredient is silica sand, about 70% of the recipe. Workers add 14% soda ash to drop the melting point, plus 10% limestone for stability. But here's the clever part. Most factories add up to 30% recycled glass to the batch. It melts at lower temperatures, cutting energy costs by 40%. Once precisely weighed, everything dumps into a specialized ribbon blender that ensures every particle is evenly distributed. Then it travels along sealed conveyor systems to the furnace. And this is where it gets intense. The furnace is an absolute beast, stretching over 120 feet long, 40 feet wide, and standing 3 stories tall. Inside, natural gas burners fire continuously at 2,800 degrees Fahrenheit, hot enough to melt steel. The flames switch sides every 20 minutes in what's called regenerative firing, where exhaust heat preheats incoming air, boosting efficiency up to 50%. Raw batch pours steadily in at 15 tons per hour. Over the next 16 to 24 hours, it slowly dissolves into molten glass. Workers monitor everything from a control room with over 50 thermocouples throughout the bath. Even a 10-degree deviation can ruin the entire batch. The molten glass gradually flows toward the conditioning zone, where temperature drops to exactly 2,400 degrees Fahrenheit, achieving perfect homogeneity. From here, different products take different paths. Let's follow flat glass first. For windows and car glass, the molten material feeds into a float bath, one of the most brilliant innovations of the 20th century. British engineer Sir Alistair Pilkington spent 7 years perfecting this process before its debut in 1959. And here's the genius behind it. Molten glass pours continuously onto a bath of molten tin, kept at exactly 1,050 degrees Fahrenheit. Glass naturally floats on tin because its density is only 2.5 grams per cubic centimeter, compared to tin's 7.3. As it spreads across the perfectly flat liquid metal surface, gravity and surface tension create glass with both surfaces perfectly smooth and parallel. The float bath stretches for nearly 200 feet. Modern lines control thickness by pulling at specific speeds. Pull faster, you get thinner glass down to 2 millimeters. Pull slower, you can create glass up to 25 millimeters thick. By the exit end, the glass is cooled to around 1,000 degrees and solidified enough to lift off without marking the surface. From the float bath, the ribbon enters the annealing layer, a temperature-controlled tunnel over 500 feet long. If you let glass cool naturally, thermal gradients would create internal stresses, making it weak and prone to spontaneous breakage. Instead, the layer cools it gradually over 2 to 4 hours. At the exit, automated cutting systems use diamond-tipped wheels to score the ribbon into massive sheets, often 10 feet by 12 feet or larger. But bottles and jars follow a completely different process. This is where the IS machine comes in, standing for Individual Section Machine. Invented in 1925, it's still the backbone of container glass production worldwide. Molten glass flows into a feeder bowl where rotating orifice rings cut the stream into precise portions called gobs. Each gob is sheared by pneumatic scissors with split-second timing, weights controlled to within 1 gram. A typical line has 10 or 12 individual sections, each making up to 4 containers simultaneously. Here's where it gets wild. In the blank mold, a metal plunger pushes down while compressed air at 40 psi blows up from below, forcing glass against the mold walls. This creates a parison, basically a thick-walled preform with the bottle's neck already shaped. Takes just 2 to 3 seconds. Then mechanical neck ring holders grip the parison, flip it upside down, and swing it to the blow mold in less than 1 second. Compressed air at 25 psi blasts through the neck, inflating it against the cooled mold walls. From molten gob to finished bottle in 8 to 12 seconds. A modern IS machine can produce up to 600 bottles per minute. Fresh bottles travel through an annealing layer for 30 to 45 minutes, cooling gradually. Then, every single bottle faces automated inspection. High-speed cameras check for cracks and defects. Infrared sensors detect stress patterns. Bottles must withstand at least 90 pounds per square inch internal pressure. Any failures get crushed and recycled back to the batch house. For specialty items like wine glasses, skilled craftsmen still use traditional glass blowing at glory holes, small openings into reheating furnaces. They gather molten glass on a blowpipe and shape it with hand tools. A master glassblower can create a wine glass in 5 to 7 minutes. Now let's talk about safety glass. Laminated safety glass in your car windshield starts with 2 sheets of float glass with a layer of polyvinyl butyryl plastic between them. The sandwich goes through rollers at 190 degrees, then enters an autoclave at 280 degrees and 175 psi for 90 minutes. This fuses everything permanently. The result? Glass that holds together when shattered. In an accident, broken pieces stick to the plastic instead of flying around the cabin. That's why windshields spiderweb instead of exploding. Tempered glass for side windows takes a different approach. Regular glass heats to 1200 degrees, then high-pressure air nozzles blast it from above and below. Surfaces cool rapidly while the interior stays hot, creating compression on surfaces and tension in the core. This makes it 4 to 5 times stronger than regular glass. When it breaks, it shatters into thousands of small cubes with dull edges instead of dangerous shards. Here's something mind-blowing. Gorilla Glass and other chemically strengthened glasses used in smartphones go through an ion exchange process. The glass is submerged in molten potassium salt at 750 degrees for 8 to 16 hours. Potassium ions migrate into the surface, replacing smaller sodium ions. Since potassium ions are 40% larger, they create a compression layer, making the glass incredibly scratch and impact resistant. Quality control combines automated systems with human expertise. For flat glass, laser scanners detect defects as small as 0.1 millimeters. Random samples undergo destructive testing. Chemical composition gets verified using X-ray fluorescence spectrometry. Everything must meet strict safety standards. The environmental impact has improved dramatically. Modern regenerative furnaces are 30 to 35% more energy efficient than those from the 1980s. And here's the crazy part. Glass is infinitely recyclable without quality loss. That beer bottle you recycle can become a new bottle, a window, or fiber insulation. Recycled glass melts at lower temperatures, reducing energy consumption by 40%. Some plants now run on 90 to 100% recycled glass. After manufacturing, flat glass often receives low-E coatings that reflect infrared heat while transmitting visible light, cutting heating and cooling costs by 30%. Container glass exits production lines at up to 1,000 bottles per minute, packed into boxes and stacked on pallets by robotic systems. The glass industry continues pushing boundaries. Researchers are developing ultra-thin flexible glass, less than 0.1 millimeters thick for foldable smartphones and rollable displays. New formulations create transparent materials strong enough for military applications while remaining optically clear. From ancient Mesopotamian workshops to cutting-edge research labs, glass has traveled an incredible journey. But at its core, the principle remains unchanged. Heat sand hot enough, add the right ingredients, and you create one of humanity's most versatile and enduring materials. So next time you look through a window, drink from a glass, or tap your phone screen, take a moment to appreciate the 4,000-year-old craft and modern precision engineering that made it possible. From sand to something extraordinary. Thanks for watching. Hit that like button and subscribe for more fascinating looks at how everyday things are made. See you next time.